Welcome to VSEPR's Chemistry Academy. Today we're going to focus on molecular geometry and the VSEPR notation. This is tied to the learning objective from College Board. The students able to use Lewis diagram and VSEPR to predict the geometry of molecules, identify hybridization, and make predictions about polarity. Now, in the VSEPR model, it is assumed that atoms orient themselves as to minimize electron pair repulsion around the central atom. Each lone pair, meaning non-bonding pair of electrons, and bonded pair of electrons around the central atom occupy a position in space which we call the domain. The Coulombic repulsion of lone pairs around the central atom actually pushes the bonded pairs closer together to form a specific molecular shape and bond angles. And it is useful in predicting molecular geometry, bond angle, and molecular polarity. So how do you differentiate between polar and nonpolar molecules? With nonpolar molecules, the bonding atoms are symmetrically arranged around the central atom. The bond dipoles cancel out each other. The center of positive and negative lie in the same place. Dipole moment is zero. With the polar molecule, the bond dipoles do not cancel out each other. The center of positive and negative of the molecule do not coincide. Now here's a chart. Let's go through that carefully. A representing the central bonding atom, X representing the atoms bonded to the central atom, and E represent the lone pair of electrons. So with the first one, VSEPR notation AX2, meaning central atom there's one and there are two bonding atoms, such as beryllium fluoride, resulting in a linear shape with a 180 bond angle, nonpolar molecule. The next one, AX3, represented by boron trifluoride, which results in trigonal-planar shape, 120 bond angle, and nonpolar molecule. The next one, AX2E, now there's a lone pair of electron on the nitride ion, which results in bent shape, less than 120-degree bond angle, and a polar ion. The next one, AX4, represented by methane, with one central atom and four bonding atoms into a tetrahedral shape, bond angle 109.5, nonpolar molecule. The next one, AX3E, one lone pair of electron on an atom of ammonia, resulting into trigonal pyramidal shape, 107.5 bond angle, polar molecule. And the next one, AX2E2, two lone pair of electron on the central atom oxygen, which is bent in shape, 104.5 bond angle, and a polar molecule. Now, all these obey the octet rules. And then the next page deals with those have expanded octet, AX5, having phosphorus as a central atom bonded to 5 fluorine atoms, resulting into trigonal bipyramidal and nonpolar molecule. And then the next one, AX4E, one lone pair electron on central sulfur atom in SF4, resulting in seesaw shape and polar molecule. Then the next one, AX3E2, central atom chlorine, 3 bonding to the fluorine atoms, and 2 lone pair of electrons, T-shaped, which is polar. Then the next one, AX2E3, xenon being the central atom, surrounded by 3 lone pair electrons and 2 bonding fluorine atoms. It is linear in shape, 180-degree bond angle, and nonpolar molecule. Then we have sulfur hexafluoride AX6, being the notation into octahedral shape, nonpolar molecule. And the next one is AX5E. Chlorine has 1 lone pair electron and 5 bonding pair to the fluorine atom, square pyramidal, polar. And then finally we have AX4E2, 2 lone pair electrons on xenon, 4 bonding pair to the fluorine, resulting into square planar shape, nonpolar. And you will need to do a lot of practice in order to become comfortable and with doing that, with writing them. Okay, explain why boron trichloride, carbon tetrabromide, carbon disulfide, arsenic pentafluoride, and selenium hexaide are all nonpolar, although they contain polar bonds. So I'm going to try to draw them over here. Boron trichloride has a trigonoplanar shape, so the bond dipole will cancel out each other, resulting into nonpolar molecule. Now with the carbon tetrabromide, we have a tetrahedral shape, and again all the bond dipoles will cancel out each other, resulting into a nonpolar molecule. With carbon disulfide, this is linear in shape with two double bonds on both sides of the carbon atom, and because the bond dipoles cancel out each other, this will be a nonpolar molecule. So when we draw the bond dipole from positive to negative, it will be pointed out like this. The bond dipole will cancel out. And then we have arsenic pentafluoride with arsenic as the central atom, one bond above it, one bond below it, one bond to the right, and one bond behind it, one bond in front of it on that imaginary triangular base that bisects the straight line, and this results into a nonpolar molecule because bond dipole cancel out each other. And lastly, the selenium with 6 valence electron bonded to one above it, one below it, with the two iodine atoms, and then on that imaginary square bisecting the straight line, you have these 4 iodine atoms, resulting into octahedral shape. Again, bond dipole cancel out each other, and there's no difference between the center and positive. They are in the same place, they coincide, therefore you have nonpolar molecules. So here's again the reasoning of what I just said earlier. Valence bond theory. A covalent bond is formed when an atomic orbital from one atom overlaps with another atomic orbital from a different atom. And the overlapping orbitals contain 2 electrons with opposite signs in spin in the ground state. In hydrogen molecule, remember each atom has a 1s1 electron, so the 1s orbital of one hydrogen atom containing 1 electron would overlap with the 1s orbital of a second hydrogen atom to form a covalent bond, represented by this electron configuration. Notice how these electrons are paired as opposite spins, and here's a diagram showing the overlap in that region contains a pair of electron in the s orbital overlap. Now continuing with hydrogen fluoride molecule, hydrogen has 1s1 electron, fluorine has ending with 2p5 electrons. So the overlap is basically between the 1s orbital from hydrogen and the 2p orbital from fluorine, housing that pair of electrons, s2p orbital overlap. Hybrid orbitals. Look at carbon. It has 1s2, 2p2 electron configuration. Theoretically, it can only form 2 bonds from the 2p orbitals, but how come it can form 4 bonds? So hybrid orbital is a theory proposed to account for the formation of the 4 bonds. Pauling, he proposed atomic orbitals on a single atom can be hybridized to form a set of hybrid orbitals that are equal in energy, and the number of orbitals formed equal the number of orbitals mixed. Imagine if you have a red flower and a white flower, and you cross them to form a hybrid flower, and that should be pink in color. So along this theory, hybrid orbitals used to describe the arrangement of electrons around a central atom account for the shapes of the resulting molecule observed. I would like to begin with sp hybrid orbitals. Look at beryllium. It has 1s2, 2s2 electron configuration, meaning beryllium really should not be able to form any bonding at all because the 2s orbital is fully filled. Well, what if one of the two pair electron in beryllium s orbital is promoted to a p orbital? And then the s and the p orbitals are hybridized and mixed to form two new orbitals called sp. Now look at this diagram. In the 2s orbital, there's a pair of electrons. The 2s orbital is fully filled, but there are 2p orbitals above it, high in energy, that are vacant. So what if one of these electrons from the 2s orbital is promoted to an empty 2p orbital and then mixed and hybridized to produce two new orbitals called sp? So the overlapping between each electron in an sp orbital of beryllium with a lone electron from the s orbital of the H atom result in two sigma bonds. Later I'm going to talk about sigma bond. It's really bonding on the same plane to account for the linear shape of beryllium hydride with a 180-degree bond angle. Similarly, we use the sp hybrid orbital to account for the linear shape of ethine and carbon dioxide. So simply put, when you have a linear molecule, highly likely it's going to have sp hybrid orbitals. So look at here, beryllium with the 2p orbitals bonding with the electron from the 1s orbital from the hydrogen, making a linear shape. Now the second type of hybrid orbitals is sp2. When one of the s orbital in an atom mixes with two p orbitals, the result is three sp2 orbitals. And when they overlap, then they form three sigma bonds. Okay, look at this diagram here. 2s orbital is fully filled, but there are two electrons, each one in a 2p orbital. If one of the 2s orbital electron is promoted to the empty 2p orbital, and then three out of these four orbitals mix to produce new sp2 orbitals, three of them equal in energy, with one in the 2p orbital remaining unhybridized. They used to account for trigonal planar shape in boron trifluoride and in ethene with a bond angle of 120. Look at this diagram. Boron in the middle forming three sp2 orbitals, and that will overlap with the 2p orbitals from fluorine, but behind the boron there's a 2p orbital perpendicular to the plane that's not bonded to anything. The other kind of hybrid orbital is sp3, and that accounts for the formation of tetrahedral shaped methane. When one s orbital mixes with three p orbitals, the resulting is four of them in equal in energy of the sp3 new orbitals with four sigma bonds in methane with bond angle of 109.5. So here's a diagram showing carbon in the middle, four sp3 orbitals equal in energy and length bonded to the four hydrogen atoms. If we look at ammonia and water, they also have this sp3 hybrid orbitals, but with ammonia, although there are four of them, one remaining not bonded to anything. So you can see there are three that are bonded to the H atom. The one on top of it just houses a pair of lone electrons with no bonding to any particular atom. That's trigonal pyramidal shape. And with water on the right, you notice there are four of the sp3 orbitals. Two of them are bonded to the two H atoms, while two of them are lone pair of electrons not bonding to anything, resulting in a bent shape. Draw a structure dot diagram for NO2 plus ion and an NO2 minus ion account for the differences in the geometry, polarity, and orbital hybridization. So here's a diagram. With the NO2 plus ion to the left, it is a linear, non-polar ion. Bond dipole cancel out each other, has sp orbital hybridization. Now with the one on the right, which is the NO2 minus the nitride ion, it is drawn as a bent ion with a lone pair of electron on the central atom end. The region of a greater electron density surrounding this end repel the bonded pair resulting in a polar ion with sp2 orbital hybridization. A sigma bond is formed when electron pairs shared in an area centered on a line between two atoms, that means on the same plane. In molecules with multiple bonds, the second or the third bond is formed from the perpendicular or parallel p orbitals to occupy space above and below the line. They are called a pi bond. Sigma bond is stronger than pi bond because it has stronger overlap on the same plane. But pi bond prevents bond rotation and will lead to structural isomers because you're trying to rotate the pi bond, actually it will be broken. Let's take a look at the benzene molecule. You'll find in your textbook that benzene is represented by two resonance structures which has alternate double single bond within a hexagonal ring, or is represented by a circle within the hexagon, like electrons are localized throughout the benzene structure. If you look at it carefully, you count there are 6 of the localized carbon-carbon sigma bonds and 6 of the delocalized carbon-hydrogen sigma bonds, adding up to 12 sigma bonds to form sp2 orbitals. And then the 2p orbital on each carbon is perpendicular to the plane, and they overlap strongly with one another, forming delocalized pi bonds. And the extended pi bond will be delocalized across more than 2 nuclei, leading to very high stability of benzene. Practice problem number 3. In the caffeine molecule, insert the lone pair of electrons in the molecule, determine bond angle at 1, 2, 3, and 4, count how many sigma and pi bonds are present, and name the orbital hybridization at central atoms of 1, 2, 3, and 4. So here's a diagram. When the lone pair electrons are drawn, 2 lone pairs on the O, 1 lone pair on each of the N atoms. And for the position 1, 2, 3, and 4, position 1 is a carbon atom, bond angle 120, sp2 hybridization trigonoplanar. Carbon number 2, similarly trigonoplanar, 120 bond angle sp2 hybridization. Nitrogen at position number 3 has 1 lone pair, trigonopyramidal, actually it's bent less than 120 degree sp2 hybridization. Then nitrogen at position number 4 is trigonopyramidal with 1 lone pair, 107.5 degree sp3 orbital hybridization. When we count carefully, there are 25 sigma and 4 pi bonds. What have we learned today? We learned how to use the vapor valence shell electron pair repulsion, the VSEPR notation, and Lewis diagram to predict the geometry of molecules and their bond angles. We learned how to identify the type of orbital hybridization, sp, sp2, sp3. We determined the type of orbital overlap according to valence bond theory. We also predicted the polarity of molecules, and we differentiate between sigma and pi bonds. From the team of MLCA, we'd like to thank you for watching and look forward to seeing you again in the next video.